Hello everyone, and welcome to our senior design presentation. We are Group 201B, the thermal team of the Stellantis EV Battery Workforce Challenge here at Cal State LA.
So this is our agenda for our presentation. For heat transfer calculations, we have Henry. For EV mandates, we have Larry. For objective and strategy, we have Juan. For analytical modeling, we have Henry. For experimental testing, we have Juan. For battery testing, we have me, Branden. For data acquisition systems, we have Heber. For simulations, we have Larry. For analysis, we have Henry. For comparison, we have Juan and Henry. And for both error analysis and conclusion, we have Henry. So the Stellantis EV Battery Workforce Challenge is a 3-year student competition in which students design, build, and test a battery pack module for the Ram ProMaster EV. The challenge is broken up into 3 different groups: the mechanical team, the electrical team, and us, the thermal team. Some important topics we use and cover are the C rate, resistance, capacity, and egen. C rate is the rate at which batteries charge or discharge. So, for example, 1C is when it charges or discharges in an hour, 2C is 30 minutes, zero point 0.5C is 2 hours, and so on and so forth. Resistance is how much a material opposes electricity flow, kind of like friction in a water pipe if we're using a water analogy. Capacity is the amount of electrical energy a battery can store in milliamp hours. And finally, egen is the rate of heat generation within a control volume, in this case the battery pack, and is measured in watts per cubic meter.
As a concern for climate change and pollution has increased, mandates such as California's Executive Order N2725 has required a 100% zero-emission EV vehicle mandate by 2035. Automakers have begun to transition their full market lineup into electrified platforms, and other states are following suit. The trend for battery electric vehicles has increased over the past couple of years and is expected to make a full market adoption within the next few decades.
So this is how the environment and system impact thermal management on the battery pack. Battery lifetime directly depends on thermal management performance. So as we can see, the battery capacity decreases as temperature increases, leading to less driving range and performance of the vehicle. To prevent this, we regulate the temperature to preserve SOC and SOH, which is state of charge and state of health. This in turn extends the battery life and reduces waste, which is especially important for batteries because their manufacturing involves hazardous materials and energy-intensive processes.
Here we have our project team. From left to right, we have Henry Solares, Juan Perez-Sias, Larry Navarro, Branden Medina, and myself, Heber Garcia. On the top right, we have our faculty advisor, Dr. Bachman, and on the bottom right, we have the thermal lead for the Battery Workforce Challenge, Arthur Espinosa.
My name is Juan Perez. This is our thermal system development strategy. Our original plan in phase 1, which was semester 1, was to design, stamp, and validate a scaled cooling plate using in-house manufacturing methods. But due to fabrication feasibility and timeline constraints, we required a shift in project scope. Our actual execution in phase 2 was using an integrated and commercial cooling plate focused on system-level testing, thermal instrumentation, analytical modeling, and CFD-based validation. For our thermal team, project objective/goals is to design, integrate, and test a subscale battery module to generate experimental thermal data for validation of analytical calculations and CFD simulation. Characterize battery and cooling system behavior under load, including charge/discharge, response, and heat generation trends. For our engineering validation approach, we're going to use 3 independent analytical methods. We're going to use analytic modeling, experimental testing, and computational simulation, CFD, so we can compare the results at the end.
Main goal for analytical modeling is to predict temperatures across the system using the resistor method. The key measurements I will be looking for are the inlet and outlet temperatures, fluid flow rate, plate temperatures, also known as my thermocouple temperatures, and battery temperatures, also known as thermistor temperatures. All of these values will be acquired while discharging at a C rate of 0.5. Is important because it allows us to predict the coolant, cooling plate, and battery without running an experiment, which is crucial for predicting the temperature rises, helping evaluate safety, and getting a better understanding of the thermal limits of the battery. The assumptions being made for the calculations are flow is fully developed and laminar with constant heat flux, 1D conduction straight through the battery, tin, and aluminum plate, constant flow, and steady state. To calculate the heat, we must know our battery's capacity, C rate, current per cell, number of batteries in the system, and internal resistance of the batteries. The current of a singular cell is its capacity multiplied by C rate, giving us 2.4 amps. Then finding the heat in the battery pack, we square the current of the cell and multiply it by the number of batteries and internal resistance of the batteries, giving us 5.18 watts of heat. To calculate the resistance of our fluid, we need to get the conventional heat transfer coefficient. Under our assumptions, that flow is fully developed and laminar with constant heat flux, making our Nessel number 4.36. The thermal conductivity of water at a bulk temperature of 21 Celsius is 0.598 watts over meter Kelvin. And finally, our inner diameter of our cooling plate is 0.00851 meters. We can plug this into our conventional heat transfer coefficient equation and get a value of 306.39. This value being units. Resistor method is made up of 4 resistors. The first one being the resistance of the battery, which is the length of these cells over 2, which factors for Egen. The thermal conductivity of the battery, area of the battery, multiplied by the number of batteries or cells in this system. The second one being the resistance of the tin, which is the length of the tin over the thermal conductivity and area for the tin. The cooling plate follows with length of the cooling plate over the thermal conductivity and area. Lastly, our resistance of fluid slash coolant, which is 1 over our conventional heat transfer coefficient, and wetted area, which is just the area that the coolant touches, multiplying it in half since only the top part of the pipe is being heated up.
For our experimental testing objective, we have one main goal, is to acquire experimental thermal data for validation of analytical and CFD models. We're going to use the execution plan of measure coolant inlet and outlet temperatures. We're going to measure coolant flow rate. We're going to monitor the battery cell and cooling plate temperatures. We're going to control the electrical loading, which is the charge and discharge profiles, and we're going to maintain constant thermal insulation. For our coolant inlet and outlet temperature measurements, what we're doing is we're inserting a thermocouple inside the tubing where the thermal reading is going to be taken inside the water for both the inlet and the outlet, and that is going to be fed into our DAC system. For our cooling plate surface temperature measurements, we have a figure on the left showing where all the thermocouples are going to be placed. We have thermocouple 1 through 5 being placed on the plate, and thermocouple 6 being placed outside of the plate to get ambient temperature of the surrounding area. This is also shown on figure on the right, where it shows the real system. For the battery cell temperature measurements, we have a figure on the left showing where the thermistors are going to be placed on the battery cells. These are thermistors which are surface mounted temperature sensors at the midpoint of each battery cell and are resistance based, and we switch them to temperature conversions, and they're going to monitor the cell thermal behavior during testing, and it's going to be fed into our DAC system.
So to test the battery pack, we need to simulate real-world scenarios by charging and discharging it with the proper devices. To charge a device, we use a DC power supply that provides voltage to a battery pack. The one we use is this model here, the Hanemetech HM305P, powered from Dr. Mr. Gibberti from the Electrical Engineering Department, and has terminals that take banana plug test leads. This is essentially the equivalent of charging an EV in our experiment. So here's a picture of the banana plugs attached to the power supply. The device on the left is the electronic load that discharges the battery that we'll talk about in the next slide. For the power supply, the maximum charging speed is 5 amps, which is not a lot for batteries that are charged up to 16 volts. So it would take pretty much the entire day to charge them from, for example, 5 volts up to 16 volts. And once the batteries were eventually charged up to 16 volts, then we would stop the charging once the amps would drop to 2.5 amps to achieve steady state of the batteries. So to discharge the battery, we used a device called a DC electronic load. We wanted to keep the C rate below 1 C for safety, and to do this, we decided to just discharge the battery pack to between 10 to 20 amps. And this simulates real-world driving conditions. So, like if you put your foot on the accelerator pedal, this essentially simulates that, where it depletes the batteries of power in order to drive the vehicle forward. So this is a picture of the entire setup during charging. But discharging, we just replaced the power supply with the electronic load. One thing I want to note is that discharging was much faster than charging, since it was set to higher amperages than charging, so that depletes the battery pack at a much faster rate. Another thing we see is that the alligator clips are attached to the battery terminals, and we cut holes in the insulator, the foam, the green foam, in order to attach them. And we'll talk about the insulation more in the next few slides.
For our plate clamp system design and integration, we have a subscale battery module was mechanically integrated with a cold plate using a compliant thermal interface material, which is a TIM, to ensure effective conductive heat transfer. A two-plate clamping system using 3/8 inch threaded rod and a compression hardware was implemented to provide uniform contact pressure and modular adjustability, as shown in the CADs, as well as the process of printing and the assembled setup shown below. For insulation material selection and justification, the purpose of insulation is to minimize heat loss and isolate from ambient conditions. It's also to enforce heat flow through the cooling plate. It also improves measurement repeatability and model correlation. For a design consideration, an R5 per inch limits parasitic heat loss with minimal added mass, is easily machined with low cost and commercial availability. It's the best performance to cost solution for this test configuration. This was selected for thermal performance, mechanical fit, and test integration. For the thermal insulation strategy and purpose, we can see the before picture where the mini module and the cooling plate are exposed to the outside surface, to the after picture where everything is enclosed in the R5 foam. This is going to minimize the heat loss, enforce heat flow through the cooling plate, suppress ambient influence, and improve model correlation and accuracy.
Our temperature readings were performed using K-type thermocouples. We sourced a National Instruments compact DAC, which was the CDAC-9174. We also sourced a National Instruments 9211 module, which is made specifically for reading thermocouples. It has 9 terminals for a total of 4 thermocouples, since each one requires a positive and negative connection. The last terminal goes unused. With the 4 thermocouples, we were able to read inlet and outlet temperature of the cold plate and cold plate temperature at 2 locations. The thermocouple data was processed using National Instruments' graphical programming environment known as LabVIEW. The dynamic data was taken from the DAC assistant and converted into an array, which was subsequently converted into a cluster of data, which is readable by the waveform chart. The waveform chart displayed live temperature readings of the 4 thermocouples. We were able to procure one more 9211 module and a new 9219 module. The additional 9211 module meant we could now read 4 more thermocouples through LabVIEW to acquire more data points. This was a major improvement from the original plan of manually logging more temperatures using handheld thermometers. This would have resulted in timing issues. Of the now 8 thermocouples, 2 remained at the inlet and outlet for coolant temperatures. The remaining 6 were systematically placed at different locations on the cold plate to better understand the temperature gradient. The new 9219 module had the ability to read 4 analog channels. These channels were used to read the outputs of 3 thermistors that already existed inside the mini battery module. Prior to acquiring the 9219 module, we were unable to take advantage of these thermistors and were unable to measure battery temperature. With all 3 modules connected to the same DAC, all our temperature readings were on the same timing. The LabVIEW code was updated to accommodate all the new sensors. The dynamic data of the 8 thermocouples and 3 thermistors was separately converted into an array. The thermistor data was then indexed through an index array. Numeric constants were inputted for indexing the 4 specific values needed. The index array outputted elements, which were then fed into formula nodes. In these nodes, the scalar resistances were converted into temperature in degrees Celsius using the beta parameter equation. These temperatures were then converted into degrees Fahrenheit. The outputs, which were in the form of elements, were then converted back into an array using build array. The resulting thermistor array and the thermocouple array were inputted into a replace array subset to the subarray and array inputs respectively. A numeric constant was then used to index the thermocouple values. The outputted array was then converted into a cluster for the waveform chart to be able to read the data. It was also separately converted back into dynamic data to be sent to write to measurement file. This feature automatically created an Excel spreadsheet of all the data each time the program was ran. Our flow rate readings were performed using a procured Hall effect flow meter rated for 0.3 to 6 liters per minute. The signal from this flow meter was collected using an Arduino Uno microcontroller. An LCD screen was used to display the live flow rate to facilitate adjustments and calibration. Without the LCD screen, flow rate could only be read through the Arduino IDE. The flow rate was processed through the Arduino Integrated Development Environment. The code received the signal and converted it into liters per minute. It also outputted the live flow rate to the LCD screen as opposed to the serial monitor output in the Arduino IDE. This facilitated the manual calibration of the flow meter. A graduated cylinder and a stopwatch were used to calculate the actual flow rate. The K-factor was then appropriately changed in the code until the flow meter matched the calculated flow rate. The change was from an original value of 588 to 1100 seen on line 10 of the code.
With the testing of the full system, you can see the figure on the left that shows everything that we just talked about. It shows the in and the out, our flow meter, our Arduino, how we're going to charge and discharge the battery, all of our thermocouples connected to the plate and our ambient temperature, our thermistors connected to the battery, and our DAC system. That is also shown on the figure on the right where it shows our real system that we created. For how we're going to process this data, we have our raw data that is implemented into a MATLAB code, which then outputs the final figures which are used in this presentation. For our experimental testing sequence, we first charged the battery to 16.7 volts at 5 amps. We preheated our battery to 90 degrees Fahrenheit. We applied our initial discharge of 0.5 C rate. We activated our cooling plate system. We logged the temperature and flow data using the DAC system, and we terminated the test at thermal steady state or at 12 volt cutoff. This test was performed under controlled conditions to evaluate cooling performance and thermal response. testing data, here we have an overview of the full system temperature profiles. Here we have the beginning of the test where we show a discharge of 0.5 C, and we see how everything reacts to the cooling plate turning on, showing a drop of T in, T out, our thermocouples placed on the plate as well as our ambient temperature, and our battery average shown. This shows the entire system heat flow. It tracks the battery, plate, and cooling path, identifies the steady versus transient behavior, and verifies sensor consistency.
As previously mentioned, there are various ways to validate models. First, there is calculation validation, followed by experiments, and lastly and most recent, simulation. Simulations allow us to validate models against our experimental ones and allow us to identify key characteristics that may not be easily identifiable, such as turbulent intensity inside a cold plate design. We must consider that simulations are highly input sensitive. Incorrect or bad boundary inputs may produce unrealistic results that sometimes look real and may lead engineers astray. The role of simulations in this project is to be one of the three validation tools and create a one-to-one model which will help the group in the future support their design decisions. Throughout the beginning of the semester, we initially created a very complex design for our simulation. In the beginning, we initially thought that this was going to make things a lot more accurate and was going to make our results better. Unfortunately, it was an overly complex geometry that was very resource intensive and very frequently crashed our computers. We were able to improve upon this design by simplifying what we did not need and also refining everything down to the first principles. We created a simplified geometry which was stable in our simulations, was easier to modify and understand, and was closer to the one-to-one scale model. Additionally, refinement levels and the actual calculation control options were definitely a factor that affected our output. Initially, we did not have refinements, but still had various issues with the simulation not completing. We were able to fix this by refining to a level 4 and setting our goals convergence to travels. We also ensured to only do a fluid flow simulation instead of a thermal one, and ensured that conduction, gravity, and internal analysis was done. The simulation properties were modeled after the experiment and calculations previously done by our group. The battery discharge rate was 0.5 C. Inlet at 0.3 liters a minute, which was exactly the same as our experimental value. Our heat output per cell was about 0.26 watts, with a total of 5.18 watts for 20 cells in total of heat output. The initial temperature was set at 90 degrees, and our thermal interface material between our cells and the actual cold plate had a thermal conductivity of 3 watts per meter Kelvin. The internal resistance of the cells were 14 milliohms. The fluid was water, internal surface roughness at 0.5, and we had an adiabatic system. The initial pressure was also at standard operating pressure. The simulation began at 90 degrees, in which, during the beginning, each cell emits 0.26 watts of heat. The water immediately begins to flow in at 70 degrees, which was on par with our experiment, and the cooling plate began to cool down until steady state was reached. The following is a temperature cut plot in which the fluid stabilizes after it hits steady state at around 72 degrees. The simulation was modeled after our experiment, and our thermocouples and point parameters were matched to around the same positioning in both the experiment and the simulation. Some of the points were placed under the battery cells, and some of them were not, just like the experiment. The simulation data here shows a plot graph of the temperature initially going up and then falling shortly. This is on par with an experimental data. However, in our experimental data, the final steady state temperatures do vary. We believe this is because of a simulation control parameter that we are still currently working on figuring out. The following is a video of our simulation cut plot. As you can see here, the simulation begins at 90 degrees and is followed by cold 70-degree water coming in and cooling the cold plate. It is good to note that this is a sped up version and does not represent real time.
Testing to analytical modeling and simulations, we need to reach steady state. For testing, we chose the intervals between 2,700 seconds and 3,300 seconds because they showed the most stable temperature behavior across the entire run. We decided to rule out T1 and T2 because they were outliers and they were not touching the plate or batteries. Averaging out the temperatures, we get an inlet average of 69.32 Fahrenheit, outlet of 69.67 Fahrenheit, thermocouples of 81.36 Fahrenheit, and thermistors of 85.15 Fahrenheit. Did the same thing for simulations, but instead chose the intervals from 128 seconds to 148 seconds, giving us an inlet average of 70 Fahrenheit, outlet of 81.01 Fahrenheit, and thermocouple of 82.77 Fahrenheit. To calculate the predictions, I had to convert the temperatures to Celsius and go from there. First, you calculate the change in temperature of the coolant by using the heat from the batteries over the mass flow rate and specific heat of water. Then you can predict the outlet temperature by adding the inlet average temperature to the change in temperature of the coolant. Next, you find the fluid temperature average prediction by adding inlet temperature average to outlet temperature prediction, dividing it by 2. Now you can find the thermocouple temperature prediction by adding fluid temperature average prediction with the battery pack heat multiplied by the sum of resistance of fluid and cooling plate. The thermistor temperature prediction is found using the same equation, except now we add the resistance of the TIM and battery.
Here's a temperature comparison of battery. This shows the testing and the calculated values being compared. For the observations we see is our testing shows stable repeated battery temperatures. Our calculated model underpredicts the temperature rise. Our simulation was not available for comparison, and this graph indicates needed for refined battery thermal modeling. For the comparison of the plate temperature, here we have the testing and the calculated values being compared. The testing shows stable plate temperatures. Our calculated model slightly underpredicts the measurement. The simulations were excluded due to excessive error, and this figure suggests the model setup requires refinement.
Here are our comparisons for outlet temperature. A few key observations are experimental data aligns closely with calculated outlet temperature. Simulation predicts slightly higher temperatures than testing. Testing shows lowest variance and tightest repeatability. All results fall within 1 Fahrenheit of each other. Here we have an error analysis for analytical modeling, where our general equation for relativity is T relative is equal to T minus T inlet average, where our general error equation is T predicted relative minus T experimental relative divided by T experimental relative, all multiplied by 100. Here for thermocouple error, we got a percentage of 11. For outlet, we got a percentage of 73%. And for thermistor, we got an error of 33%. Although this model isn't perfect, it provides a strong foundation that can be tuned and refined to meet industry standards for battery thermal management.